Lynn Roy LaMotte is a professor at Louisiana State University Health Center, USA. His topic of presentation is on experience with multiple solution from MLE algorithm for mixed model. Another speaker is Julia Volkova. She is a professor emerita at Louisiana State University Health Sciences Center, New Orleans, USA. She will deliver talk on application of one of Rao Mitra's matrix diagonalization theorems. We are happy to have you here. I now request Manjunath Prasad to chair this session.
Thank you, Raksha. Just some time back, I got a message from Dr. Ravi Shankar that he is traveling and cannot join us. So I'm chairing this session on his behalf. First of all, Professor Lamotte will be delivering his talk, and then Professor Julia Valova. I also got a message from Professor Julia Valova that she will try her best to join as she is experiencing some problem with the network. Anyhow, we'll see whether she will be able to join us or not then later. First, I invite Professor Lamotte to join us, and please. So.
I want to begin by thanking the organizers for giving me the opportunity to give a small talk for a big occasion, and that is honoring Professor Rao on his 100th birthday. Professor Rao's influence pervades, it permeates all of almost all of statistics, particularly though in the area of linear models, where he made significant original seminal contributions to the foundations that now are so widespread in practice. So again, it's an honor for me to be able to participate in this occasion, and I heartily wish Professor Rao the most happy centennial anniversary. The developments that began in the 50s and 60s that led to widespread use of linear models and linear mixed models, multivariate linear models, and so on, were rather sophisticated in both the mathematics and in the computations, the numerical analysis required for realizing results in linear mixed models. The first algorithms began to appear in statistical computing packages, not in full flower, but they began to appear in various forms in the early packages, SAS, SPSS, and so on. They were developed over the years. The advent of the mixed models procedure in SAS in the early 1990s was a real watershed event. I can remember people around me celebrating when that particular version of SAS came out that first included what's called proc mixed, and celebrating that they were running some big data set that involved a split plot design with random subplot effects, and it only took 6 hours to run. So this was quite an event. Those algorithms have been broadened, made more versatile, applicable in wider array of situations, of course, over the years, to the extent that now we can find them in almost any package with syntax that allows us to adapt to a tremendous variety of situations in terms of factor effects and multivariate and time series and that sort of thing. And the use of them has become easier and easier. The interface, the user interface has become simpler and over the years. So the now use of very complicated analytical procedures in mixed models, the use is practically simple. We can analyze reasonably big sets of data with complicated models at almost the stroke of a few keys. And I'm saying that because I think, in a way, it's too easy. And when when such an algorithm runs and doesn't generate any red messages in the log and no warning signs, I think by now we tend to accept it as okay. Everything is fine. As long as it didn't give us any error messages, that's great. I'm ready to publish the results. What I want to illustrate today is a situation in which I found, in that sort of routine application, I found almost by accident that the results were in fact not correct. They were suboptimal. The algorithm is based on maximum likelihood estimation, and as you'll see, it turns out that the likelihood function can have multiple stationary points, and there's nothing in the algorithm that distinguishes those, and so you cannot, in fact, be confident that you have found the global maximum. So here's the setting, though, requires some introduction and explanation. This is the setting in which I have encountered this, and that's inverse prediction with a multivariate response. And so here's the setting of inverse prediction. We have an experiment in which subjects often, and what I've been working with is in forensic entomology, so these are larvae of flies, and in an experiment they're sampled at each of several predetermined ages, so we know the age, observe the response, multivariate response like length and weight, and that over n independently sampled subjects at specified ages. That's the training data, and then we're presented with a mystery specimen, the response vector of a mystery specimen, and we'd like to know what its age is. So the objective is simple: given the training data and models relating the training data to some parameters and the response of the mystery specimen, make inference about the age of the mystery specimen. Now, the models that I'll be dealing with here are as simple as possible. For the mean vector, I'll be using a straight line model. It takes this form, where B is a matrix of regression parameters. Predictor variables, X, fixed known function of T, its vector value. Shorthand notation for the means and the predictor variable at age T sub I. We'll talk about two models for the variances. So in a fixed effects model, the variance or the variance covariance matrix is fixed, but comprised of unknown parameters. Or it's linear in a set of variance covariance parameters. So we'll either talk about constant variance covariance matrix or one that is not constant, that differs with factors in the setup. In each of these z's, like the x, is a fixed known function of t. Often these are formulated as spline functions, linear splines, cubic splines, that sort of thing. But here they're going to be super simple, and I'll make that more specific as we go on. So the unknown parameters are the regression coefficients and the variance components. And with only those, this would be a classical linear mixed model. The parameter T star, the unknown age, occurs in a way that is not linear. So with that, this is not truly a linear mixed model, not linear in all the parameters. However, given T star, for a fixed known given T star, we just have n+1 observations at known ages, T1 through Tn and T star. And that, in terms of the parameters for the mean vector and the variance covariance matrix, is a mixed linear model. So the statistical computing packages that exist can be used directly if we can adapt the syntax to this particular set. Any such program can be tricked to get a p-value for each specified value of T star by testing a particular linear hypothesis in terms of a parameter vector, which I'll denote as delta. And all this is augmenting the model for the mean vector with dummy variable times this R vector delta. That's equivalent to testing that the mean vector in the population from which the mystery specimen came is given by the model for the mean for the training data. The test statistic takes the Carl Pearson form, so an F statistic that just looks like the vector of the residuals at T star, weighted by the inverse of the variance covariance matrix of those residuals, that quadratic form, where these are estimates of the various parameters. So this is fairly straightforward. And the p-value then is computed from a central F distribution with appropriate degrees of freedom. Now I'll use constant degrees of freedom in the illustrations here. In practice, one might use the Phi Cornelius generalization of Satterthwaite or the Kenwood-Roger approximations to denominator degrees of freedom, but I'll use only fixed denominator degrees of freedom here. When the variance covariance matrix is considered to be or modeled as constant, then the form of that test statistic can be simplified to look like this. And T star shows up in here only here and here in this X of T star and C of T star. And the others, the B hat and the sigma hat, come from the training data only. They don't involve the mystery specimen. The mystery specimen only shows up here as Y star. And so some further simplification can be obtained from that. However, I want to go ahead. The likelihood function will assume multivariate normality, and the profile likelihood function then is the supremum over the parameters B and sigma. This is now for the case of fixed sigma, fixed but unknown, of the likelihood function of the plus indicating the n+1 observations. That can be simplified to this form here. So it only involves the determinant of this matrix, sigma hat plus T star, based on the n+1 observations as if T star were known. And that determinant can be simplified algebraically. Remember, the profile log likelihood is monotone decreasing of this determinant. This determinant, in turn, is monotone increasing in that test statistic, F of T star. So that means that the profile likelihood function is a decreasing function of that test statistic F, which in turn means that it's an increasing function of the p-value. And so that means that the maximum likelihood estimate of T star is the maximum p-value estimate of T star, which is intuitively very pleasing. But there was a fair amount of algebraic manipulation involved in establishing that. But it is proved in that case. Now the question is it also true when the variance covariance matrix is not modeled as being constant? I've tried to prove that. I've tried to see whether I could prove or disprove it. And maybe you could have more success than I, but I certainly haven't been able to prove it. And so I set out to investigate this relation, whether the maximum likelihood estimate was the same as the maximum p-value estimate numerically. Actually, I was hoping to find a counterexample, a convincing counterexample, so that I could quit worrying about trying to prove it. The models I use that I'll show you here, the mean vector I've modeled simply as a linear interpolate between, I'll just use a range from 0 to 10 for t. And so the mean vector is just a linear interpolate of a mean vector at t equals 0 and a mean vector at t equals 10. And likewise, the variance covariance matrix is just a linear interpolate of variance covariance matrix at age 0 and 1 at age 10. So very simple, and I'll illustrate with a 3-variant response. So that means that there are 6 parameters for the mean vector, and there are 12 parameters for the variance covariance matrices. So that's 18 plus the 1 for t star, 19 parameters. Even in this simple situation, it seems like a large number of parameters to be dealing with, and that's the dimension of the domain of the log likelihood function. The profile log likelihood function is defined this way, and in the same way. However, I can't get an expression for it, so I set out to evaluate it numerically. So over a grid, a fine grid of t star, just to compute the maximum. Well, each one of those computations involves an application of a mixed models algorithm. Proc mix is what I used in SAS. So I used a grid that had 176 values of t star, and it's required for both the full model and a restricted model. The p-value comes from the full model as the p-value for the test that delta is equal to 0, and the likelihood comes from the restricted model. And so that's twice 176 runs of a general linear models procedure. So the computations do begin to add up. The example I'll illustrate here is this data set, 31 observations, 30 in the training data, and 1 mystery specimen with a trivariate response. Now, behind the scenes, I can tell you this mystery specimen actually came from t star equal to 5. But we have to pretend that we don't know what its age is. So a little explanation is necessary how these algorithms work. Proc mix is basically a Newton-Raphson algorithm, and given given a theta j, so the parameter vector, that's 19 components, or well, we'll use 18 here. We're fixing t star. It approximates the log likelihood function of second order approximation, and finds the new value of the parameter that maximizes that second order approximation. The quadratic part of the approximation can either be the Hessian matrix, the matrix of second partial derivatives, or the negative of the information matrix. That's called Fisher scoring when that's used. And Fisher scoring gives a concave approximation, so it's locally increasing around the current point. SAS proc mix, I have to mention this because that affects convergence, and SAS proc mix permits choosing an application of Fisher scoring for the first m iterations. So you can say never, so m is 0, or 1, or 10. I use that 0, 1, 10, or 1,000, and default. In various places, SAS says default is same as 0, but I've seen runs where that is in fact not correct. So in any case, convergence is affected by lots of things, convergence criteria that the user chooses and so on, but in particular, it's affected by the choice of M and the starting point. Now these algorithms generally will choose a starting point, a theta naught for you, or you can designate one. In these applications that I'm describing here, using the default often led to problems of convergence and infinite likelihood and that sort of thing. I found that it performed much better if I gave it a starting point. Now, the only starting values we need are for the variance covariance components, the sigma naught and the sigma 10. I found that I got convergence almost always with this specifying both of these as identity matrices. Now remember, I'm doing this over a grid, 176 grid points. And it's only by that I discovered that we don't always get optimal results. And you'll see as soon as I get to the pictures. But that's the idea, evaluate the log likelihood over this grid so that I can see what the profile log likelihood as a function of T star looks like, maximizing over all the other parameters. For starting values, as I said, I used either that both of these are identity, or what I'll call forward. I used the solution values for these variance components from the previous step just to the left. And backward, I started from 10 and worked back down to 0 and used each for the starting point, the one just above it, the solution from the one just above it. So the starting points, the grid's fine enough. The starting point should be fairly close to the solution for the next value of T star. That was the rationale. I'll show you the figure. I'm going to come back to this. And most of the results are our own view here, but I have to explain what they are. These top curves are, so the scale here is T star, 0 to 10. The top curves are for the full model. That includes that dummy variable for the mystery specimen. I'll come back to that in a minute. The middle curves here are for the restricted model. Remember, this is the likelihood function that I'm interested in. I want to see where its maximum is and see where the maximum of the p-value is. These are p-values. Now, the p-values are all computed from the full model likelihood function, basically. This is the picture I'm showing you here is for 10 initial steps of Fisher scoring. But I also did for 0, 1, 100, and 1,000. So there's this picture for other specifications of Fisher scoring. The light gray line is the maximum of all of those likelihood functions examined for all levels of Fisher scoring. So in fact, in this picture, if we look at the likelihood functions, we see this is the default. So based on default starting values, and suddenly it has a kink here. That's very suspicious. Another kink here, and then a big drop here. Backward, you don't see the green for forward because it's under this black. The backward starts up here at 10 and uses previous solution as starting point as it moves this way. And you see it gets quite different results for the likelihood function. And you can barely see there's a little piece of green here. So the green is there, and it differs from so the forward differs from the backward only right here. But further, there was another value of the Fisher scoring, which gave this gray likelihood function up here. So there's a lot going on here, and I recognize that. Now the p-values, again, the green p-value, this one, comes from the green likelihood up here for the full model, and the red from the red, and the black from the black. And you can see it looks like the green, the forward, is above the other two, except right here at the end. But there's no guarantee that any of these is actually the maximum. This is maximum among the ones we looked at, among the Fisher scoring and starting value results that we looked at. The vertical lines indicate where peaks occur, and the solid lines, you really can't see them. So the gray, this is the maximum overall, peaks at a solid line between two dashed lines here. The red, you can see, that's for the likelihood. The solid lines are likelihood. The dashed lines are p-values. The red p-value, you can see peaks here, and so on. And of course, the whole objective is to see whether the likelihood peaks at the same place as the p-value peaks. But there are three different p-values here. Of the ones we see, the green, the green seems to be the best, and it has the smallest p-value. But these things, I've looked at many of these, many settings with pictures like this, and this one is fairly nice. It has not too many anomalies compared to others where they go all over the places. So the point to be seen here in terms of maximum likelihood is that just because you get a result in each of these points on each of these curves is one run of a mixed models algorithm. Just because you get a result doesn't mean it's right. We can see here that this one, the result that led to this value of the log likelihood, looked perfectly good, but there is, it's suboptimal because the log likelihood actually can be higher. We found a point at which it evaluates higher. We don't even know if this is the maximum though for that particular value of T star. So, for value of T star at 3.1, so roughly here, if you look vertically here, I looked at that as a place where there are three different solutions. So the default or constant gave these estimates of the variance components, forward gave these, backward gave these. And immediately you see that even the scale seems different. These estimates, this column doesn't look like that, doesn't look like that. They're quite different estimates of the variance components. The full model log likelihoods are actually quite, seemingly quite close, but and the p-values for the backwards is 0.08, and for forward and default, it's 0.01 plus something. So different than if we were really, if we were using a cutoff of 0.05, then we'd be led to different inference with the backward than with the forward or default. But in emphasizing ordinary use, we don't know. We see the results of one run, and if nothing seemed to have gone wrong, I think we tend to accept it. And that's the point of my illustration here. It ain't necessarily so. There is a question. Here we have three different solutions. Are they even local maximum? So I briefly tried to look at that. I'll explain this. So this is, the curve being plotted here is the log likelihood function, the profile log likelihood function. Now there are 3 points there. So I looked at the line connecting the D to the F, the D to the B, and the F to the B, and drew lines through those and extended them slightly. So for instance, the green line here starts at the D estimate of the variance components and goes over to the forward estimate of the variance components, which turned out to be the best, right? So if you follow the green, and I extended the line a little bit past each of those points. So it's one line going between two multidimensional points, but extended slightly out past them. So I could see the shape of the function. And in this case, you can see the green, it's very, very steep. And then it looks like may even be a singularity that's causing that peak there. But then it decreases quite a bit and then goes up to what looks like a pretty benign local maximum here. And if we look at the red, that goes from default to backward. And also, it seems to have a nice local maximum here. So it gives us an idea. But it's clear that it's not, the problem isn't that the log likelihood is flat, which is often quoted as a problem in convergence. It's not flat. It goes way down from here and then back up in each of these cases. And so its behavior is fairly complicated. And that brings me to the conclusion of this. My point was, within the context of inverse prediction, multivariate response, to illustrate what I ran across in trying to see whether the maximum p-value estimate of T star was the same as the maximum likelihood estimate of T star, which is what happens when the variance covariance matrix is modeled as constant. But when it's not constant, does that hold? I have to conclude it's not clear yet whether it holds. I don't have a good solid counterexample. If we look back at this, where these peak are very close together, so close that it could just be truncation error. So I'm still looking for a counterexample or a proof of that fact, which would be very tantalizing. And with that, I'll end. Thank you very much for your attention.
Thank you, Professor LaMotte.